Some physicists believe our universe may exist inside a black hole. The idea sounds absurd at first, but the deeper modern physics goes, the harder it becomes to completely dismiss it. Black holes already distort time, bend space beyond recognition, erase information, and push gravity to limits where the known laws of reality begin to fail. And hidden inside those equations is a strange possibility. A collapsing star may not simply die. Under the right conditions, it may create an entirely new universe beyond the event horizon, possibly this one. Black holes are often described as objects, but they behave more like regions where reality itself starts breaking apart. Near them, ordinary intuition becomes useless. Time slows down. Light curves, distance stretches. Cause and effect begin behaving strangely. A black hole does not pull things in the way a vacuum cleaner does. Instead, space-time itself collapses inward so severely that every possible future leads deeper toward the center. Even light eventually runs out of escape routes. The boundary surrounding this region is called the event horizon. Crossing it changes something fundamental. From the outside universe, objects falling toward a black hole appear to move slower and slower. Their clocks stretch, their signals fade. To distant observers, they never truly seem to cross the horizon at all. They become frozen near the edge, dimming slowly into darkness as the universe around them continues aging. But from the perspective of the falling observer, nothing dramatic happens immediately. They continue inward, and this creates one of the strangest disconnects in all of physics. Two different observers witnessing completely different versions of reality simultaneously. To one observer, the traveler never fully enters the black hole. To the other, they already crossed it long ago. Both perspectives appear mathematically correct. Somewhere inside this contradiction, space-time itself begins losing coherence. At the center of a black hole, Einstein's equations predict a singularity, a point where density becomes infinite and the curvature of space-time becomes endless. Physics cannot properly describe conditions there because the equations destroy themselves. Infinite values appear everywhere like warning signs. The known laws of the universe stop functioning. And yet singularities may not truly exist. Many physicists suspect the singularity is not a real object, but evidence that our current understanding is incomplete. Quantum mechanics and general relativity, the two most successful theories in science, completely fail to cooperate under these conditions. Gravity dominates enormous structures like galaxies and black holes. Quantum physics controls tiny particles and microscopic uncertainty. But inside a black hole, both systems collide violently. Reality enters territory no human theory can fully map. This is where the idea becomes unsettling. Some models suggest the crushing collapse inside black holes may reverse under extreme quantum conditions. Instead of compressing matter into an infinitely small point, space-time itself could rebound outward. The collapse would transform into expansion, a new universe emerging from gravitational death. From the outside, the parent universe would only see a black hole. But beyond the event horizon, an entirely separate cosmos could begin inflating into existence. Stars forming, galaxies spreading, time beginning, observers believing they are witnessing the birth of everything. And if this process is physically possible, it raises an uncomfortable question. What if our own Big Bang was not the beginning of reality? What if it was simply the interior of another universe's black hole? The similarities are difficult to ignore. The early universe existed in an unimaginably dense state. Space-time expanded rapidly from extreme compression. Matter, energy, and time itself emerged from conditions where ordinary physics breaks apart. The mathematics describing black holes and the mathematics describing the Big Bang begin resembling each other in strange ways. Some researchers have proposed that every black hole may contain a hidden expanding universe disconnected from its parent reality. Each universe could create more black holes inside itself, generating even more universes beyond those horizons. A kind of cosmic reproduction, reality endlessly creating new realities through collapse. An infinite chain hidden behind gravitational darkness. If true, this would completely change humanity's place in existence. Our universe would no longer be unique or isolated. It would become part of a vast hidden structure extending far beyond observable space-time. Entire universes could exist inside black holes scattered across larger universes we could never access or even detect. And somewhere beyond our own cosmic horizon, our universe itself may appear as nothing more than a dark sphere suspended in another reality. But the deeper implication becomes even stranger, because black holes do not only destroy matter, they appear to challenge information itself. In physics, information is not just knowledge. It represents the exact arrangement of particles, energy, and quantum states that define reality. According to quantum mechanics, information cannot truly be destroyed. The universe preserves it absolutely, but black holes seem to erase it completely. Anything crossing the event horizon disappears behind a boundary that can never communicate outward again. If a black hole eventually evaporates through Hawking radiation, as Stephen Hawking predicted, then what happens to all the information trapped inside? For decades, this became one of the greatest paradoxes in modern science. If information is destroyed, quantum mechanics breaks. If information survives, black holes cannot function the way we thought. And this paradox opened another terrifying possibility. Some physicists now suspect reality itself may function more like a projection. The holographic principle suggests the information describing a three-dimensional region may actually exist encoded along a distant two-dimensional boundary. In simple terms, the universe may behave like a hologram generated from deeper informational structures. The idea first emerged from black hole thermodynamics. Physicists discovered that the amount of information a black hole can contain appears proportional not to its volume, but to the surface area of its event horizon. That should not happen. Ordinarily, more volume means more storage space. But black holes obey different rules, as if the true description of reality exists written along surfaces rather than inside space itself. Some researchers believe this principle may apply to the entire universe. Everything humans experience, space, time, matter, gravity, even consciousness, could emerge from deeper informational processes occurring beyond ordinary perception. Reality may not be fundamental. It may be generated, and black holes may be the places where this hidden architecture becomes visible. Near them, time stretches toward infinity. Space folds inward. Quantum uncertainty dominates geometry itself. The universe starts exposing seems normally hidden beneath ordinary life. The deeper scientists examine black holes, the less stable reality appears. Even causality becomes uncertain. Inside rotating black holes, some equations predict paths through space-time that loop backward into the past. Wormholes may theoretically connect distant regions of space-time together. Quantum entanglement links particles instantly across impossible distances. Certain interpretations of physics suggest space-time itself may emerge from entanglement networks woven beneath observable reality. And somehow, black holes sit directly at the center of all these mysteries. Like wounds in the structure of existence, silent regions where the universe accidentally reveals too much about itself. The frightening part is not simply that black holes exist. It is that they seem connected to nearly every unsolved problem in physics. Gravity, quantum mechanics, information, time, consciousness, the origin of the universe itself. Again and again, the equations lead back toward darkness. Toward horizons humans cannot cross and return from, toward regions where the distinction between beginning and ending starts dissolving completely. And if our universe truly exists inside one of these structures, then the night sky may look very different from what humanity assumes. The galaxies surrounding us may not drift through empty space at all. They may exist inside the interior geometry of something far larger. Our entire observable universe, every star, planet, ocean, civilization, memory, and human life, could exist inside a hidden gravitational structure embedded within another reality we will never see. A universe inside a universe, a cosmos born from collapse. And beyond our own cosmic horizon, another level may exist above us. Another universe, another sky, another civilization staring into darkness, wondering what black holes truly are, not realizing they may already be living inside one. If the universe truly exists inside a black hole, then the most disturbing part is not the origin of reality. It is what that possibility says about time itself. Because inside black holes, time does not behave normally. In some regions, it slows almost to a stop. In others, the future and the past begin losing their clear separation. And near the center, physics predicts conditions so extreme that the normal flow of existence may completely collapse. This means the universe may not simply exist inside a black hole spatially. It may also exist inside a kind of distorted temporal structure where our understanding of beginnings and endings no longer applies. Near an event horizon, gravity becomes so intense that time stretches dramatically. This is not science fiction. It has already been measured experimentally around Earth using atomic clocks. The stronger the gravity, the slower time moves relative to distant observers. Around black holes, this effect becomes extreme beyond ordinary imagination. A person orbiting close to a supermassive black hole for only a few hours could return to find that centuries passed elsewhere in the universe. Entire civilizations could rise and disappear while they experienced only moments. The closer one moves toward the horizon, the more severe the distortion becomes. Eventually, time itself appears to freeze from an outside perspective. This creates a deeply unsettling implication. Somewhere near every black hole exists a boundary where the external universe effectively sees eternity unfolding all at once. Matter falling inward becomes trapped in a kind of endless slowing process. Signals redshift into darkness. Motion dissolves into stillness. Black holes seem to sit directly at the edge between time and timelessness. And some physicists suspect this may connect to the birth of universes themselves. The early universe expanded faster than light immediately after the Big Bang. Space itself inflated violently in fractions of a second. During this period, the known laws of physics behaved under conditions almost impossible to reconstruct today. Time as humans understand it may not have existed in any meaningful sense before this expansion stabilized. The deeper cosmologists investigate the first moments of existence, the stranger the timeline becomes. There may not have been a true beginning, only a transition. Some theories suggest the Big Bang was not the creation of reality from nothing, but a bounce from a previous state. Instead of an absolute starting point, the universe may cycle endlessly through collapse and rebirth. In these models, black holes become gateways between phases of cosmic evolution. A collapsing universe could compress into extreme density, then expand outward again into a new space-time region. The process would erase almost all traces of the previous cosmos, leaving observers inside believing they are witnessing the true beginning of existence. But the chain itself may extend forever. No first universe, no final universe, only endless transformation through gravitational collapse. This becomes even stranger when quantum mechanics enters the picture. At extremely small scales, reality behaves probabilistically. Particles exist in uncertain states until interaction forces outcomes into stability. Empty space itself is not truly empty. Quantum fields constantly fluctuate beneath reality, generating temporary particles that appear and vanish continuously. The vacuum of space is alive with invisible instability, and black holes interact violently with these fluctuations. According to Stephen Hawking's calculations, black holes slowly evaporate over unimaginable stretches of time through quantum effects near the event horizon. Tiny particle pairs constantly emerge from empty space. Normally, they annihilate instantly, but near a black hole, gravity can separate them before they reconnect. One particle falls inward while the other escapes as radiation. Slowly, impossibly slowly, the black hole loses energy. Eventually, after periods so long they almost lose meaning, even supermassive black holes may disappear. This raises another terrifying possibility. If black holes eventually evaporate, then perhaps universes inside them remain disconnected forever from the parent cosmos that created them. Entire realities could survive long after their originating universe fades into cold darkness. Civilizations inside these hidden universes would never know they originated from another layer of existence, just as humanity may never know. And the more scientists study black hole entropy, the more reality begins resembling information rather than physical substance. Entropy measures disorder, but it also measures informational complexity. Black holes contain enormous amounts of entropy concentrated into finite surfaces. Somehow, Their event horizons encode staggering amounts of information. This led physicists toward one of the strangest ideas in modern science: the holographic principle. According to this framework, three-dimensional reality may emerge from lower-dimensional informational boundaries. Space itself could function like a projection generated from quantum information encoded elsewhere. If true, depth may be an illusion. Volume may be emergent. Reality may not fundamentally exist the way humans perceive it. Black holes first revealed this possibility because their informational behavior breaks ordinary assumptions about geometry. The information content of a black hole scales with surface area rather than internal volume, suggesting space-time itself obeys hidden mathematical rules unlike anything in everyday experience. Some researchers now believe the entire observable universe may function holographically. Everything humans touch, see, remember, and experience could emerge from deeper informational structures existing beyond ordinary perception. And black holes may be places where this hidden framework becomes exposed. Near them, space-time loses stability. Quantum behavior invades gravity itself. The distinction between physical objects and abstract information starts dissolving. Reality begins looking less like matter and more like computation. This connects to another disturbing idea. Some physicists have compared the universe to a quantum simulation, not necessarily artificial, but informational at its core. Reality behaves mathematically with astonishing precision. The laws governing particles resemble encoded rules. Space appears quantized at microscopic scales. Quantum entanglement links distant particles instantly through hidden relationships untouched by classical distance. The universe increasingly resembles a system processing information beneath visible existence. And black holes may act like the deepest processors in that system. At the center of galaxies, supermassive black holes shape entire cosmic structures. Their gravity influences star formation, galactic rotation, and the distribution of matter across millions of light years. Without them, galaxies may not stabilize properly at all. It is almost as if black holes quietly organize the architecture of the cosmos from within. Invisible engines shaping reality itself. And this leads to an even darker thought. If universes emerge from black holes, then perhaps black holes are not accidents of physics. Perhaps they are necessary mechanisms for reality to reproduce, evolve, and continue existing across endless layers of space-time. Some cosmologists have explored theories resembling cosmic natural selection. Universes that generate more black holes create more offspring universes. Physical laws favoring black hole production become more common over vast cosmological timescales. In this picture, reality itself evolves. Universes giving birth to universes through gravitational collapse. Natural selection operating across infinite layers of existence. Humanity would become part of a process unimaginably older and larger than civilization, biology, or even stars themselves. And yet, despite all these theories, the center of a black hole remains hidden forever behind the event horizon. No information can directly escape. No observer can return with answers. The universe protects the truth behind permanent darkness. This silence becomes deeply unsettling when combined with another mystery: consciousness. Modern physics still cannot explain why awareness exists at all. The equations describing particles, forces, and space-time never fully explain subjective experience. Somehow, collections of atoms become capable of observing the universe and questioning their own existence. Matter begins looking back at itself. And in a universe built from information, quantum uncertainty, and hidden dimensions, consciousness starts feeling less isolated from the structure of reality itself. Some interpretations of quantum mechanics even suggest observation plays a fundamental role in determining physical outcomes. Before measurement, particles exist in superpositions of multiple possibilities simultaneously. Observation collapses uncertainty into definite states. Reality stabilizes through interaction. No one fully understands why. But if observation participates in shaping physical reality, then conscious beings may be woven more deeply into the universe than humans realize. And inside a black hole universe, this becomes haunting, because it means awareness itself may emerge naturally from collapsing space-time structures. The universe creating observers capable of questioning the universe. a self-aware cosmos unfolding inside gravitational darkness. Perhaps this is why the night sky feels strangely emotional to human beings. Vast silence stretches in every direction. Ancient light crosses billions of years to reach Earth. Black holes lurk invisibly between galaxies, bending space-time without mercy. And somewhere beyond all visible stars, deeper structures may exist entirely beyond comprehension. The terrifying part is not simply that humans are small. It is that reality itself may be infinitely layered. Universes inside universes, horizons beyond horizons, each level believing itself complete while hidden inside something vastly larger. And if our cosmos truly exists inside a black hole, then the darkness surrounding us may not be empty space at all. It may be the interior architecture of something alive with forces we were never meant to fully understand. A structure so enormous that entire civilizations become microscopic events inside its geometry. Human history reduced to brief electrical patterns flickering inside a collapsing cosmic system. And beyond our universe, outside the horizon we can never cross, another reality may continue expanding under entirely different laws of time, matter, and existence. A larger universe surrounding ours the way oceans surround a drop of rain. Silent, infinite, watching from beyond the horizon while humanity drifts unknowingly through the interior of a black hole. Black holes were once thought to be simple endpoints of collapse, regions where matter falls in and never returns. But modern physics no longer treats them as final objects. Instead, they appear more like transformations in space-time itself, where familiar rules do not break so much as change into something we are not yet able to fully describe. The turning point came with Jacob Bekenstein's work in the 1970s. He proposed that black holes must carry entropy, a measure of hidden information. At first, this idea seemed almost impossible. Entropy was associated with heat, disorder, and physical systems, not with objects from which nothing escapes. But Stephen Hawking's later calculations confirmed something even stranger. Black holes emit radiation. They slowly lose mass over time. They are not eternal. They evaporate. This discovery immediately changed their nature. A black hole was no longer a static void, but a thermodynamic system, something that evolves, something that can store information. And if it stores information, then the question becomes unavoidable. What does that information go when the black hole disappears? This question leads directly into one of the deepest conflicts in theoretical physics, the black hole information paradox. Hawking originally suggested that information might be permanently lost, but this idea clashes with quantum mechanics, particularly the principle of unitarity, which says information must always be preserved. This tension forced physicists to reconsider what black holes actually are at a fundamental level. Gerard T. Hooft and Leonard Susskind pushed this problem into a radically new direction. They proposed the holographic principle, that all information contained in a volume of space can be represented on its boundary surface. This idea was not philosophical speculation. It was derived from black hole thermodynamics itself. In black holes, entropy scales with surface area, not volume. That single fact suggests that the deepest description of reality may not exist inside space, but on its edges. Juan de Sena later formalized a version of this idea in string theory through the ADS/CFT correspondence. In certain mathematical universes, gravity inside a volume of space is equivalent to a quantum field theory on its boundary with no gravity at all. Two completely different descriptions, one with depth and curvature, one flat and lower dimensional, turn out to describe the same physics. This suggests that gravity itself may not be fundamental, but emergent from deeper informational structures. At this point, black holes stop being just extreme objects. They begin to resemble the key that exposed this entire hidden structure. They are where physics becomes self-referential, where space-time begins to describe itself through limits. And once this idea is established, cosmology begins to echo it. If black holes encode reality on their boundaries, then the universe itself may behave in a similar way. The observable universe has a horizon defined not by gravity, but by expansion. Light from beyond a certain distance can never reach us, no matter how long time passes. This creates a cosmological boundary that behaves mathematically like an event horizon, not because space is collapsing, but because it is stretching faster than information can travel. This similarity has led some physicists to explore whether our universe might itself be an internal region bounded by a larger gravitational structure. Nikodem Poplawski, working within Einstein-Cartan theory, proposed that black holes could generate new universes through torsion in spacetime. Instead of collapsing into singularities, matter could reach a maximum density and then rebound, forming an expanding spacetime region on the other side of the horizon. In this view, every black hole becomes a transition point, not an end, but a hidden beginning. The interior of collapse transforms into expansion. What falls inward in one universe could emerge outward in another. The Big Bang, then, might not be the absolute origin of everything, but the internal result of such a process. Lee Smolin extended this even further through the idea of cosmological natural selection. In his model, universes that produce more black holes are statistically more likely to generate offspring universes. Over immense timescales, this would create a kind of cosmic evolution, not biological, not intentional, but driven by the reproduction rate of spacetime itself. Physical constants would slowly drift toward values that maximize black hole formation, because those universes simply survive more often in this branching structure. In parallel, loop quantum gravity, developed by Carlo Rovelli and Smolin, suggests that spacetime is not continuous at all. Instead, it is composed of discrete quantum loops. Under extreme conditions, such as inside black holes, these loops may resist infinite collapse. Instead of forming singularities, spacetime could reach a minimum scale and then reverse direction, a bounce instead of an end. This idea connects directly to cosmological models where the universe itself may have originated from such a bounce. Roger Penrose's conformal cyclic cosmology also explores a related structure, suggesting that the extremely expanded future of one universe could become mathematically equivalent to the initial conditions of another. In this sense, black holes may act as transitional structures within a much larger cyclic geometry of time itself. What emerges from all of these theories is not a single answer, but a convergence. Different approaches, general relativity, quantum mechanics, thermodynamics, and information theory, begin pointing toward the same pattern. Reality behaves as if information is the most fundamental ingredient, and spacetime is the structure that organizes it. Even the concept of a singularity begins to dissolve under this perspective. Instead of infinite density, modern approaches increasingly treat singularities as signs that our current theories are incomplete. Quantum gravity is expected to replace them with finite, structured transitions, regions where spacetime changes phase rather than ending. And inside that transition, something even more unsettling appears. If black holes are informational boundaries, and if boundaries define reality itself, then every observer exists inside a region defined by what cannot be accessed. Knowledge is always horizon limited. We never observe the full structure, only projections filtered through causality. This is where the holographic principle becomes more than physics. It becomes a statement about perception itself. Reality, as experienced from within, may always be a reduced projection of a deeper structure that cannot be directly seen. And if our universe is itself inside a black hole, then even the cosmic horizon is not just a boundary of observation. It may be the edge of a deeper encoding process that defines everything we can ever experience. At that point, black holes are no longer objects in space. They are the mechanism through which space becomes understandable at all. And the closer we look at them, the less they resemble things, and the more they resemble instructions for how reality is constructed in the first place.